Thank you for being here bright and early on Friday morning. Let's start the session. Our speaker today is Professor AFrishman from the Department of Physics, Technion, and she'll be talking to us about 2D condensate from 3D waves in rotating turbulence.
Thank you so much for the introduction, and thank you to the organizers for inviting me. Yeah, so this is what I'm going to talk about, and this is work that has been done by Sebastian Bowman, who's a postdoc in the group. Doing very hard work. Okay, so I'll talk about a few flavors of turbulence in this talk. So the first flavor of turbulence that we know about is 3D turbulence. So the usual picture is you have large scales, energy injected in large scales, and then you get smaller and smaller scales. You have a direct energy cascade. There's also 2D turbulence that you're also probably familiar with, where you have a large scale, you have inject energy at some scales, and then it goes to larger and larger scales. So small scales generate large scales, and this is what we call self-organization. And what I'm going to talk about in this talk is about 3D turbulence that behaves like 2D turbulence, not because it's very thin or in the limit of 3D turbulence, but because there are waves in it. So an outline, just because I will start with an introduction, and maybe for the specialists it will be boring, so to kind of let you know what I'm going to talk about. So the first part is going to be an introduction where I introduce 2D turbulence and explain why there's an inverse shape. Probably you're familiar with it, but I'll just mention the argument. And then I'll talk about 3D rotating turbulence and talk a bit about the waves that you can see there and the interaction between the waves and the 2D component of the flow. And then I'll focus on our focus, which is considering a rotating flow in steady state when there is a condensate. So I'll tell you what a condensate is with 3D forcing. And what I'll try to explain is why energy goes from 3D to the 3D condensate. And I'll talk about the high rotation limit and show that the condensate gradually disappears using sort of ideas from wave turbulence. And then I'll talk about the low rotation regime, and I'll show that there is a coexistence between direct and inverse transfers of energy. So that's the plan. Okay, so first 3D turbulence. Okay, that's the picture. You have energy at some scale. You have a flux of energy. Energy is conserved. So you have a large Reynolds number in these scales. The interaction basically conserve the energy. So the only thing you can have is a flux of energy. Small scales, and at small enough scales, you can have dissipation and the energy leaving the system. So that's a classical picture. Now, in 2D turbulence, you also have energy that's conserved, but you have additional conservation loss, again, in this limit of zero viscosity and no driving. So this additional conservation comes from the fact of vorticity having special properties in two-dimensional flows. So you can think about the vorticity as twice the angular velocity of a fluid element, the average angular velocity of fluid element. And in 2D, it's always parallel to, right? It always points out of the plane. And by conservation of the angular momentum in the z direction of fluid elements, which is true also in 3 dimensions, and it's just a reduction of Kelvin's circulation theorem, then if you assume a 2-dimensional incompressible fluid, then you get an additional conservation law, quadratic conservation law, which is called the entropy. Okay, so, and of course, there's different variants of 2-dimensional flows. You don't have to assume that it's incompressible. If it's not incompressible, you get a modified conservation law, but the origin is the same. Okay, so we have two positive definite quadratic conservation laws. So energy is conserved. You can write it in K space as energy spectrum, right? So the energy in the K mode, K here is the magnitude of the vector, and the entropy, and the two are not independent, right? Because in the end, we just have one field, the velocity field. So the entropy, if you Fourier transform, is just K squared times EK. So the amount of energy in both K in shell K is EK, and the amount of entropy is K squared times EK. Okay, so we have two conservation laws, and we know that the consequence of that is that we'll have fluxes, right? Because we have this range of scales where there's conservation of energy. There's conservation of energy. Okay, so we might expect that we'll have a flux of entropy and we'll have a flux of energy. But there is a contradiction. Why? So let's assume there is a flux of entropy, let's assume there is a flux of energy in small scales. In that case, we'll have a finite amount of energy at large scale. Now I'm taking the Reynolds number to be as large as I want. This means that I have some kind of UV or thing that goes to infinity. So I can make my K arbitrarily large. So I can have, if I have finite energy at arbitrarily large K, this means that I'll have a floating amount of entropy that goes Ks. Okay, so that's a contradiction. So it has to be that the flux of energy to small scale or large K goes to zero as K goes to infinity. Okay? And I can still have a finite flux of entropy to small scales. And this implies that instead of a flux, right? So you don't have a flux to small scales, but at these scales, there's no dissipation. So something that happens with this energy, there are nonlinear interactions. So these nonlinear interactions, instead of taking the energy to small scale, they will take the energy to large scales. Okay? So in this 2D system, we have a direct cascade of entropy to small scales and a reverse cascade of energy to large scales. So these are the two cascades. And usually, the way that we present this picture is that you have K space, and then the kinetic energy or entropy. You have forcing scale, and then you have entropy going to smaller scales until the cutoff is related to capacity, and you have energy going to larger scales, and there is an IR cutoff, so there's a cutoff that has to do with the system size. Okay? So the way the energy balance works is that you have dissipation at small scales of the entropy, okay, and the dissipation of the energy goes to zero, and you have the excess energy goes to larger and larger scales. And one question is what will happen to that energy? So if your dissipation rate at large scales is not that slow, then it can be arrested somewhere. And so you compare let's say, usually if you're in 2D, the main dissipation is by bottom friction, so it gives you a rate. You compare it to the eddy turnover time at a particular scale, and you see which one is faster. So if the dissipation rate is faster, then you will dissipate that scale. But if you can make the dissipation rate arbitrarily small, then you will have energy going all the way up to the box scale. And what will happen to it is that it will accumulate at those larger scales. Okay? So there will be a lot of energy at K that's approximately 1 over L. And that's called a condensate. Okay? And the idea is that how can when will I stop accumulating the energy? When the amplitude of the condensate is large enough so that even though the dissipation rate is very slow, I can take a small fraction of a large quantity and get a finite dissipation of energy. And this way I can have a balance of energy in my system. Okay, that is the amount of energy that I'm injecting will be equal to the amount of energy being dissipated by the condensate. I'm sorry that this is here, this is the length square. See, I see it. Okay. It's not just dirt on the wall. Okay. So the idea is that if you start, so this is the pictures from an experiment. If you look at the screen, you see it from the research group in Australia. So they looked at a thin layer of fluid. It's an electrolyte. You drive a current through it, and you have a magnetic array of opposite polarity. And that generates small-scale vortices, and then you increase the friction with the bottom as much as you can by introducing a patient layer to another layer of another fluid below this one, below the electrolyte, and then you watch as time goes by. Then what you can see is the buildup of the large scale flow. Okay, so this is what's called a condensate. Okay, and you may ask, okay, so this is not an inverse cascade, because when we talk about a cascade, we're thinking about things which are local in scale, and the energy balance here is actually different. It's so it's inverse energy transfer because it's going from the fluctuation that introduced in some scale to the large scale flow that's over here. And the way that the energy gets dissipated is by the condensate. Okay? So the interactions are what we call quasi-linear, and we have talked about it. So it's direct interactions between small scale and this large scale condensate. And there's scale separation between the condensate turbines. Again, we take this limit of forcing scale very much separated from the box scale, and this is the limit where you expect universal things. So once we're read some ideas of summarize what you can do theoretically, and other people's work as well. In this setup, you can read this paper. Okay, but this is not the subject of this talk. The subject of this talk is, can we see something like an inverse cascade in 3D? So meaning that we have a three-dimensional system, and it's not a thin layer. Okay? I'm not working in a limit where all the kinetic energy is in the 2D component. That's not the situation that I'm thinking about. Okay, so what am I thinking about? I'm thinking about rotating in 3D flows. Okay, and it's a known fact that energy piles up in 2D large scale. That energy piles up in 2D large scale. So I introduced the energy at some scale. Okay, and eventually it reaches the large scale and 2D scales. And there's actually experimental quantification of really, you can measure how the inverse cascade develops in this system. Okay? And this is a system from the Shalom group in Jerusalem. And they're forcing it by introducing jets of water. Okay, they're rotating it very quickly. Okay, so what you see here is the development of these structures. You can see that they're growing in size. Okay. So this is known. And then you can also ask, okay, I want to focus on this condensate. So again, the condensate is something where you have an inverse cascade, you have dissipation that's slow enough, and then you have buildup of energy at the larger scale. You form these large scale flows. So these ones, it seems harder to get them although I'm going to you can. But you can get them in situations, and I think maybe there's one for So this is very nice work. Under convention, so you don't have to do any internal forcing, you have this very convention, and they were able to go into this regime where you observe these large scale vortices that form. Okay? And then, of course, there are other groups that observe them then also with there are different boundary conditions. There's issues there. Because you have a lot of these patient boundary layers. So if you get rid of them, it's easier to get these condensates. And then there's a question if you can get them without these. So that's okay. Okay, so a question is, so why does the energy pile up in the 2D large scales? Okay. So one hypothesis is that we know when we get inverse cascade, it's when we have additional conservation laws. So are there any additional quantities that we've missed that are conserved in 3D? And well, probably more, that is also conserved. So you can go into a helical basis. So basically a basis in Fourier, which diagonalizes the curl operator, and then you have two modes with positive or negative curl of the mode, and then gives you negativity modes, which can be either positive or negative. So it can be composed negativity into K times the positivity mode times the negativity mode, and the energy is just sum of the two energies. Okay, so great, we have the conservation law. Why doesn't that? Well, does that give us And in the reverse cascade, we know there is a reverse cascade, so probably not. And of course, it's known that it doesn't. And the reason why is that it's not closely tested. So the same kind of argument of saying energy flux goes to small scales, and then I have the energy is the sum of the two of the plus and minus modes, and that makes energy. And the argument before was, well, if these things are finite, then these modes grow, I mean, the electricity in the plus and in the minus can go to infinity, is unbounded. So we have contradictions here. Of course, we do not have contradictions because the two can grow at the same time, right? So the positive is and the negative is and they balance each other. So that sum is always remains finite. Okay, so this is not.
Are you going to specify anything about the Rossby number?
Oh, yeah. So far, yeah. Okay. So I mean. That's not the answer, right? So what's special about rotation? And of course, it cannot be the answer because you have basic conservation also in 3D without rotation. So there must be something special about rotation. So what is special about rotation? What's special about rotation is that you have waves. Okay, they're called inertial waves. And these waves happen to also diagonalize the helicity. It's not surprising if you think about the real force, like the okay, so there are modes that have very positive helicity, or they carry very indefinite helicity, either positive or negative. And each helicity mode propagates either upward or downward propagating. Should be up and down. Okay, and they have this anisotropic dispersion relation. So twice omega. So omega is the angular velocity with which you're taking. Stationary KZ is the wave number in the z direction. The total wave number, right? The magnitude of the wave number, and is this number which can be either plus or minus 1. So for plus, it will go plus, for minus, it will go minus, and that changes the changing of the wave. Okay, so these are the properties of the waves. Okay. Okay, so yes. Thank you. Is it? Yes, thank you. Okay, so we talked about 3D turbines, we talked about 2D turbines, and now we have another type of turbines, which is wave turbines. Okay, and those are subject. And we are going to use really something minor from all of this. Okay, so the main idea that we agree is that when you think about interactions between waves, if you're in a regime where the wave frequencies are fast, then the only interactions you have are resonant interactions. So think about the energy, right? And the energy transfer between modes, right? So we have these interactions are cubic, right? So that's why you have frequencies here. So you have frequencies here, and you require that the sum of the frequencies adds up to 0, because otherwise, if you go into the spaces of these waves, you will get an oscillating factor that cancels them, cancels the interaction term. Okay, so that means that when X is not satisfied, we expect that the interactions between the modes would not exist. Okay? So interactions are restricted to resonant ones. And I guess you know this also from class talk this week. Okay. But 2D modes, they have 0 frequencies. They're not actually waves. Okay, because the wave frequency depends on KZ, and KZ is equal to 0 with 2D modes. Okay, that's the definition of 2D modes for me. So that means that they're not waves. And there's a general result that says that 3D waves then cannot transfer energy to 2D modes through resonance. Okay, so if you assume this resonance condition, then what you get is that the transfer coefficient between 2D, the transfer coefficient from 3D to 2D just goes to 0. Okay, so there's no energy that's being transferred between these two manifolds, between 2D manifold, which is 0, and the 3D manifold. Okay, and there's a nice general argument that that shows you that whenever you have two constant quantities and this strange frequencies, it basically comes from the fact that if this frequency is zero, like the transfer coefficients are actually proportional to the frequency in that sense. So if this frequency is zero, this transfer coefficient also has to be zero. Okay, so you kind of can use this idea that when you have zero frequency waves, you have certain quantities that constrain the energy transfer. Okay. Okay, so that means that 3D modes and 2D modes couple, right? Because you cannot transfer energy between them. Okay.
Yes.
So in particular, that means that if you have a rotating, fastly rotating, and of course, Pat, I'm not saying anything about gross speed so far, so I'm just being very wavy. So if you have rotation and you inject energy in 2D, then it stays in 2D. Okay? So if you have a 3D flow, you inject energy in 2D, that energy in 2D will not interact with 3D modes, and so there will be an inverse cascade. Okay, so this explains everything you wanted to know. So maybe I should go. But no, why not? Why doesn't it solve the puzzle? It doesn't solve the puzzle because it's actually well known since the word was that energy, even when you inject the energy into 3D modes, it still reaches 2D modes. Okay, so it's not the situation that we're injecting most of the energy in the 2D modes. It's a different situation. We're injecting the energy in 3D modes. So in particular, I mean, if you think about this, yeah.
You need 3 poles 2D and 3D mode.
Generated. Yes. Yes, I'm saying if I inject my energy into 2D and I don't have rotation, then I will develop instabilities. That 2D flow will develop instabilities, and those instabilities would be 3D, and these 3D flow will just will have a general, like a normal cascade of energy. And now I'm saying, okay, introduce. I don't understand my question. Okay.
Yes.
Sorry?
Yes.
No, but when I'm talking about 2D, I'm just saying most that are in. Okay, maybe I should have. You're right. I should have said it more. So what you see, this is a 3D. I don't know if you can see very well, but this is a 3D flow. Okay, it's a 3D box. But what you can see is that it's pretty much uniform in Z direction. So its KZ is pretty much zero. So that's what I mean by 2D modes. I should have said that before. Yes. Okay. So these are just modes that are completely independent of the Z direction. Of course, if you find out, you will always have sound scale which will have change. They could be in the top. You have a scale independent Z direction.
Yes, 3D mode.
Yeah, sure. They can be generated. Yes. So, okay. So the point is that if you think about the earlier nerve, then surely you're not injecting energy into 2D modes, right? And the same goes for Aaron's experiment where you have jets that are you're releasing jets and sucking back into the flow, and there is nothing 2D about it. It's really 2D. Okay, so this means that even when you inject energy, and this was sort of quantified here more recently, that really you do see that there is a transfer of energy from 3D wave modes to 2D modes. Okay, so this is, I think you can treat it as a empirical fact. Okay, so what are the puzzles then? So one puzzle is how can the waves transfer energy to 2D modes? Okay, so 3D modes here are waves. That's what we've learned. And also, we've learned that in this wave turbulence framework, when we're only considering resonances, there are no interactions between 3D and 2D modes. They just couple. So the question is, how can they transfer energy? And then the other question is, why is the energy transfer always from 3D to 2D and not the opposite? Why is that?
Okay.
So what we're going to consider, and this is again inspired by David's work, it's just easier to take an elongated domain. And for reasons of symmetry, this is such an elongated domain, what you get are the jets. Instead of vortices, and it's just these the same because it's Cartesian. And then instead of the more complicated systems that they do, which is like rather than not, and have instabilities and everything is sort of self-generated in the flow, what we're going to do is we're just going to use 3D forcing that's external, so it's just white noise that injects energy at some scale, which is not the largest scale of the box, it's about a mode 10 or something like that. Okay, so we can control the energy directly, and most of the energy is input into 3D modes and not into 2D modes. Okay. And then the more quantitative question that we like to answer is it goes back to what that is, and this is, okay, we have actually at least, what, 5 dimensionless parameters in this problem. So we have the Rossby number, which I define on the Forsen scale. We have the Reynolds number, which again I define on the Forsen scale. And then we have also the aspect ratio. So my aspect ratio is actually not the same in Y and Z. So this is a box that's, it has the same height as X, but it's elongated in Y. Okay, so it's not right, it's not quasi 2D in that sense, but it has this aspect ratio just to get the jets. Okay, so there are these 5 dimensional parameters, and the question is, how does the state, basically the observable is, there is some energy that goes into the condensate, and we'd like to understand what's the functional dependence of that energy on these parameters. Okay, so the first thing that Sebastian did when we came is to run a bunch of simulations, which takes a long time because you need to meet a steady state. We did not introduce friction here. We were just working with viscosity. It's also simpler for some reasons, which also I learned from your analysis. Okay, so the thing that you can look at first is the energy in 2D. Okay, so this is U squared, but that's the energy in the 2D modes. Okay, and you can as a function of Rossby number. So there's a few things that you can see here. So there's one confusing thing in this community, and that's the fact that as you decrease the Rossby number, the rotation increases, which is not very intuitive. So over here you have just plain old 3D turbulence. Then what happens as you increase the Rossby number, the amount of energy that reaches the 2D manifold increases. Okay, that's what we might expect. But then it also decreases back. So that's also maybe something you could expect, but we'll try to explain it quantitatively. Okay, so these are the observations, and we'd like to understand what's going on here. And just to give you kind of a picture of what's going on, so this is 3D turbulence here. Here, there's a region where you have, so all these squares are condensates, which look differently in different places. Okay, and over here you have these circles. Okay, I should say, these circles are places where actually you have coexistence. You have both a 2D condensate. If you start from a state in condensate, but if you start from 0, then you actually only get inertial waves, which also gives you a hint maybe of what's going on. Sorry. Okay, so the first thing to understand is how does energy get to the 2D manifold? And there are different ways that can happen. And the way that I'm arguing that it happens is on this figure. So if you look at the energy fluxes and you decompose them into, so the black line is the total flux, and green is 3D reading, red is 2D, somewhere there, but not that big, and then blue is 3D 2D. Okay, so this means that the energy gets transferred by direct interactions of the condensate, this large scale flow, with 3D modes. Okay, so that's the conclusion from this plot. And you see that the transfer is here. This is energy where the transfer is reversed. Okay, this is a Rossby number of the condensate. Okay, so negative means energy goes to the condensate from small scales to large scales. Okay. So I'm actually not going to really introduce the theory, and everything is going to be a bit more hand waving, but We do have a quantitative theory, and the way kind of the principles behind it is, well, first we use quasi-linear interactions. So we're saying that the main interactions are condensate and two waves, and wave interactions are not important for this. We also assume that the condensate occupies a larger scale. So we're just working with one mode in the box. And then, for example, we're computing the Reynolds stress, but we're just computing one mode of the Reynolds stress that corresponds to this one. And then, very importantly, we also use scale separation. So the typical wave numbers of the wave, which are T, and ky, which is the wave number of the condensate, the ratio between them goes to zero. So you're in this limit where everything, in some sense, for the waves becomes local. It's very non-local for the condensate, but for the waves, it's very local. And that makes theory easier. Okay. So we know from wave turbulence that if we have fast rotation, then interactions have to be restricted to be close to resonance. So what does that mean? It means that the sum, so for the condensate there is zero frequency, so it means that for the wave, the sum of the frequencies has to be zero or close to zero. Okay, it can't be really exactly zero because exactly zero makes sense, but it can be close to zero. Okay, and that's one of the things we quantify. Okay, but that implies that you can only have interactions between wave and condensate only for same helicity waves. Okay, so if the waves have a different helicity, then they're off resonance and they don't interact. Okay, so you can see that by taking this relation, plugging this in, you see that you get PZ plus KZ, so you get PZ times S plus QZ times S, and so that implies like that happens on the same side. One over P equals one over Q. Okay, so you can only have interactions between same density waves. Okay. On the other hand, the condensate is large scale. So the helicity transfer between the condensate and the waves can be neglected. It's very small. Okay? And that means that the wave's helicity is actually conserved. So for each sign, it's conserved. The total is conserved, but also for each sign. Because they cannot exchange helicities, right? They do not interact with opposite helicity waves. They only interact with the condensate. And the condensate actually does not really transfer. I mean, you don't really transfer helicities to the condensate because it's large scale. And another way to think about it is that you have an adiabatic invariant in the system, or you can think about it that helicity for each sign of the wave is a wave action, which is conserved. Okay. Okay, so now we have that on the same time helicity wave interact, and the wave helicity is approximately conserved. So this means that we have additional conservation laws, which are now positive definite. So it's H plus and H minus. Okay, so this means that when we inject helicity for either sign, we have a flux that goes to small scales, and that means that for the waves, the energy at small scales has to go to zero. Okay, there cannot be a flux of energy for the waves to small scales. Now, what can happen instead is that you could, in principle, you could transfer the energy to small scale, to large scale waves. But that actually doesn't happen because what the mean flow does, it advects in phase space, right? So it generates, through the advection and through the shearing, it generates smaller and smaller scales. So you would not have the reverse process here. So what happens is that the energy has to go somewhere to large scales, and that somewhere is the condensate. Okay, so this explains, right? So that is the picture that you inject energy and helicity into the waves. The helicity, there's an helicity flux to small scales, and then that prevents from energy of the waves going to small scales, and instead it goes to the condensate. And I'm sure you're familiar with this sort of process where, like, you have action conservation, and the frequency is decreasing as you go to larger case, so you have to transfer the energy to the condensate to large scale flow. Okay. Okay, but if this is true, what I told you, if all the energy goes to the condensate, then we can do an energy balance, and we can predict that the amplitude of the condensate, so this would be the shear, the RMS of the shear, would look like this. And this means that if we go to low enough Rossby numbers, so high enough rotations, then we should see a constant. And actually, the whole kind of this whole thing also came from another work which I read by Kolokolo in 2020, where they did actually this computation. So I mean, they actually computed the Reynolds stress in this framework. They didn't really comment on the fact, and they got the result that all the energy goes to the condensate, to the 2D flow. They did not comment on the fact that it has to do with conservation of elasticity. But kind of, it looks like all the energy has to go there. But we know that cannot actually happen. But we have also another, I mean, a different flavor of the same sort of computation. Okay. But that's not what we see, right? We don't see, like, if what I told you is correct, then what we should see is that, okay, for different Reynolds numbers, the amplitude should increase or decrease, whatever. And then it has to plateau, right? Because there's a constant there. U prime squared should be equal to a constant. So it should not depend on the Rossby number, but it does. And so why is that? Okay. And the reason for that is this condition that we said, that the interactions have to be close to it. Okay? But we have to specify this condition a bit more carefully. Okay? So let's try this condition more explicitly. This is still, I mean, here I wrote an equal, but it should be approximate. So this is an approximation. And there are corrections to it. One wants to take care of, we'll go very approximation, okay? So you can approximate the sum of the two frequencies for the same mass, because they're equal to minus using as the difference between the frequencies. Okay, and that's very small in the sense that this is the condensate wave number, which is a very small number in some sense. But we have to compare. So we have two waves, and there's a leading frequency. There's a difference between their frequencies. Now we either want to say that the frequency difference is very small or it's very large. If it's very large, then there will not be any interactions. If it's very small, the interactions will be there. But what does small and large mean? The only sense in which they're small and large is compared to some other time scale which has to do with the energy transfer. Now here our interactions with the 2D flow are through this mean shear. So the transfer time has to do with this prime RMS. Okay, so this is the typical rate with which interactions happen. And that tells us that what we have to do is we have to compare the difference in the frequencies to this shear rate. And if okay, so now I'm going to be so if this is larger, if the frequency difference is larger than the typical time over which we have transfer of energy, then they will actually be correlated. Okay, so for each mode, we have to check. Right? It doesn't only depend on this omega, which is your rotation rate. So it doesn't only depend on the Rossby number, or sorry, it doesn't depend on the Rossby number, but for different waves, you have different conditions. And you have to select the waves, the only waves that can transfer energy to the condensate are the ones that now satisfy these conditions, where their heating frequency is small enough. Okay, so that gives you a condition and the modes that can transfer energy to the condensate. And that implies that actually the quality that you should have, so this is the dissipation of energy through the condensate, right, through this dissipation. And this is, I mean, this is a function. So we have epsilon d over epsilon. This is just the name of the energy that's being transferred to the condensate, and that depends on u prime over omega, as you can see here. It also depends actually on the ratio between the forcing scalar and the watt, but I don't write it here. Okay, so what actually appears here by the computation is the Reynolds stress times u prime. Okay, so this is the production or usually called production term. Here it actually brings the energy to the condensate. Okay, so what that tells us first is that now we can actually divide everything by this omega squared. And write everything in this form. And now, using this variable of u prime over omega, I'm going to use u prime, which will be epsilon squared. This is the square root of epsilon over u divided by 1 over omega. And you can think about it as roughly times for 1 half. Okay, so this gives us an equation which is a function of u prime over omega and depends only on rho squared epsilon. And you can use this representation to collapse the graph. Okay. And again, this idea of using this is actually coming from the follow-up paper. That's again, how to use it in this way. That's okay. So what we see is that we have the data, which is u squared function of rho, but then when we plot it as a function of rho epsilon, then we have this collapse. Okay, and in particular, what you can do is you can have actually a relation. So if you know, so one thing you can compute is when is this condition not met? I mean, when is it true that for all the modes that I'm forcing, I'm never going to go off resonance? Okay. So this means that I have to take Pz and Py to be the largest that I can. And if the largest that I can is not satisfied, then I get that all the modes transfer energy to compensate. And then that gives me epsilon, which is 0.1 for our system, but it depends on the ratio between the forcing scale and the box scale. Okay. And another thing you can do is if you're in this regime where this u prime over omega is small, like if you're increasing the rotation rate, then this is roughly linearly on 1 prime over omega. So what you're doing is you're summing over all the modes that can contribute. And if you go to the limit where there are modes, then this function is roughly linear modes. And in that case, what you get is the scaling, so it's easier to solve for u prime over omega squared, or u prime over omega, so these and this cancel, so you get a Rossby squared dependence. There isn't a huge ring here, but it seems consistent with what we're seeing here. Okay. So this is a story. This was a story about what happens to modes that are as you increase rotation, and you lose the energy in those that are resonant. But you can also ask what happens when I decrease rotation. What happens here? Okay, and what happens here is you can actually again break this condition in a different way. Okay, so before I told you that waves with different velocities cannot be resonant. But that's not quite true. I mean, the condition for them to be resonant is that twice the frequency has to be much smaller than 1 over u prime. Okay? And in principle, what happens in the system is that you're sheared by the mean flow. So you're generating smaller and smaller scales. If you're generating smaller and smaller scales, then this speed is becoming larger and larger and larger. So this frequency is becoming smaller and smaller and smaller. And so eventually you will be able to satisfy this condition. So what I'm saying is that if you start off only being able to interact with the same density modes, eventually what you will develop is that break this condition. Okay, so you will be able to mix the positive and negative waves. Okay, and this is what you actually see is that, and I should say, yes. No, so I didn't say. I mean, I'll say it in a minute. I'm sorry. I mean, I didn't say there is. So the condition is different, right? So before what we had is different elasticity, same elasticity, and this condition then gives you the derivative of the frequency. But now, if I'm assuming that it's the opposite elasticity, then this condition gives me twice the frequency. Okay, and usually twice the frequency, if I'm at fast rotations, the Rossby number is small, so this would be a restrictive condition. But what I'm saying is that eventually, I mean, I do go to scales where this condition can be broken. Okay. So in particular, what you can see in this plot is that so here you can divide into sectors. So this is not so here it's a little bit different than what I'm going to do next, but you could look at the energy transfer. So basically the rate of stress that's coming from same helicity modes transfer energy to condensate. And this part is negative, meaning it transfers energy to the condensate. And then if you're above some Rossby number, or here 0.1 or so, 0.2, what you see is that you develop this direct escape, this direct transfer, as I say, this transfer of energy that has to do with these plus minus modes. Okay, so once I introduce interactions, because I decrease rotation, I allow for waves to interact with different helicity modes. Then what happens is that I develop now processes which take away the energy from the condensate instead of giving it to it, giving it to the condensate. Okay, and a different way to look at it is to look at it actually in phase space. So what we're plotting here is this is Py and this is Cv. And what's shown here is the calculation from analytics of the energy transfer from these different nodes. Okay, so what's happening? So you're forcing a history of KF. Okay, when you see red, it means that you're transferring energy from the waves to the condensate. So over here, your frequencies are such, so if we increase rotation, we only have these transfers, and the only type of interactions that we have are between same and helicity modes. Okay, so plus plus or minus minus. So same and helicity modes and the condensate. But then once we decrease rotation, there's a line, so this line, which is exactly this condition, which tells you that once the energy, right, so what happens is that you have a flux of energy that's going to small scales, or a flux of helicity that's going to small scales. Okay, it's vanishingly small. But if once it reaches this scale, then actually what happens is that you are back to having interactions between opposite helicity modes, and now you're basically going back to the regular shear flow, and you can extract energy from the mean flow. And actually the nice thing is that you can in fact compute exactly how much energy you're taking away from the condensate in this region. Okay, because evidently linear shear is a really simple system. Okay. Okay, so that's the picture, and this line, the slope of this line, is exactly the shear rate divided by omega. Okay, so what happens is that on the one hand, for each u prime over omega, I can compute how much energy the condensate will get. Okay, and this has to do with what's the size, or how much energy does the sector that mixes the helicity extract from the condensate versus how much energy does the sector that conserves the helicity, same sign helicity, gives to the condensate. And that is controlled exactly by the shear rate. So the shear rate self-tunes to have an energy balance.
So the line goes like the frequency size. So
yeah.
Your condition is
sorry, yes, it should be right. Sorry. Yeah, exactly. Yeah. The drawing is correct. Whatever. Sorry. You're right. Whenever. Okay. So and this is something that you can compute. And you show that most of the energy extraction is coming actually from modes which have a large PZ but a small kx, and the process is sort of so you have the vorticity of the condensate, and it's being tilted in the y direction, and that gives energy, that gives vorticity to the to the fluctuations, so it generates energy for the fluctuations. So small kx dominates because then you spend the most time in these regions where you have it's the slowest interaction, basically. Okay. So now you can close the system because you know that this is coming from this is the value that you have. So the dissipation of energy in the condensate has to be equal to the energy that you transfer from the waves, and that depends also on U prime over omega. So you can close this system and get a solution for U prime over omega. And this is what is plotted here. Okay. So this does not connect to this because here we're not taking into account the fact that there can be decoupling. Okay, so we're not. There is some region where you have an overlap and where you also have you're losing some of the energy from the homochiral sector. Okay. So two features that you should. Oh, sorry. So I should say that when the epsilon goes to 0, then this dominates, and you're actually back to the relation that we had before. Here you read that U prime over omega is equal to corresponds to U prime equal to square root of epsilon over mu. And in the other limit, so it will connect to fully homochiral. Everything is homochiral. All the interactions are only same chirality. And in the opposite limit of rho the epsilon going to infinity, now you should recall that rho the epsilon depends both on Rossby and on Reynolds. So I can extend it to infinity if I have a very large Reynolds number. Okay, so it doesn't necessarily mean that the Rossby has to go to has to be large. Okay, so what happens in that limit? So there's work from Sakis that shows that the condensate has now an amplitude which is proportional to the rotation rate. Okay, and from this equation, you can actually see how that comes about. So this is the state where basically Reynolds number is very large. So the dissipation of energy, by the condensate is very slow. Okay, it goes like 1 over Rossby minus 2. And that state actually there is such a state with a finite condensate. So the condensate doesn't have to go to 0 for that. Why? Because you have another source of dissipation. Okay, so you have energy being transferred to the condensate from the homochiral sector and then being taken away from the condensate by these LDC mixing sector. So you don't have to have, even in the limit of Reynolds number going to infinity, where the dissipation by viscosity is small at the large scales, you have a source of dissipation. So the condensate in that state would self-tune into a particular value of U prime over omega. Right? So this would be so it will be proportional to omega with a factor which we find should depend on the ratio between the box scale in X and the Portman scale. So for us, this is order 1. So that's why we get this order 1. That's right. How many?
5 minutes.
Okay, good. Okay. So I don't have time to talk about what's happening here. So the saturating state, of course, it cannot go on forever. There should be a difference in the end between taking Rossby epsilon to be large by increasing the Reynolds number or by increasing the Rossby number. Right? If I increase the Rossby number, I should eventually lose the condensate. If I increase the Reynolds number, I evidently do not. Okay, and what happens then is, so we don't have a quantitative theory, but we do have a sort of idea of what happens there is that this U prime over omega decreases because basically you start feeling the scale where the modes are not rotating anymore. So you have a cutoff where you don't feel the rotation anymore, and then cutoff comes close to the homochiral sector. And okay, so in a sense, what's happening here is that you don't have enough waves to energize the condensate in some sense. Okay. So what are the open questions? Okay. So what I didn't explain is how is the condensate doing that? Okay, and in particular, how to explain the inverse cascade and the 3D transfer without a condensate. Now, I think that it might be something similar to what I talked about here, in the sense that you have some place in wave number where the 3D and the 2D can connect, so you can transfer energy from 3D to 2D, and then once it reaches 2D, it does the inverse cascade. Okay, so here the interactions were dominated by this 2D, 3D because there was a large-scale flow, which dominated things. But in the case that when we don't have that, then I expect that because also people really observe the inverse cascade, then I think it has to do just with 2D, 2D interactions, and the role of 3D is just to find a place where you can leak the energy to the 2D manifold. Okay, and another thing that I haven't discussed is that actually, if you go, sorry, someplace, yes, okay, here, there were also stars over here, which I didn't talk about, and these stars actually correspond to flows which are not jets, they're vortices. And these ones have, I mean, even before these vortices appear, you actually have a symmetry breaking between the jets. And these ones, of course, also have symmetry breaking. You see there are only cyclonic vortices here in the sea of negative ethnicity. So explaining here, I think there's an interesting question of what selects the scale of these structures and how they're sustained. And I think it's not unrelated to what happens in benefit action and scale selection there. Okay. So summary. What I showed you is that these 2D large-scale flows get energy from 3D waves, and that has to do because of the separate conservation of each time for the waves. And then for fast enough rotation, the condensate correlates from the waves gradually. And for a slow enough rotation, the mixed time interactions are allowed for some of the waves, and those extract energy from the condensate. Yeah, and maybe take small messages. Well, the role of conservation, well, you obviously know, but another thing is that the waves can alter interactions. So you generate new conservation laws because you have the waves and you're just using wave turbulence. Because they have finite time scale separation, right? So all phenomena that I showed you was because there was a finite time scale separation between the shear rate and the rotation rate, and that gives this rich transitional region. With that, thank you for your attention.